Hi Spring fans, welcome to another installment of Spring Tips. I think about scaling software a lot, right? Because obviously scale is a function of architecture, and to the extent that we can pre-plan our architecture, we can pre-plan our ability to scale. Obviously there are constraints on our architecture, obviously things like cost and time and so on, but in general, it's a thing you can pre-game before you actually get into the game, right? And it's useful to be prepared. It's useful to go into this prepared. And one of the things that people talk about is, can Java scale? Can it do a good enough job? Obviously, this is true, right? I mean, the largest companies on the planet do what they do with Java. It's not possible to do what they're doing otherwise, right? So Amazon, Google, eBay, Facebook, etc. All these companies are using, at scale, Java. Or, in the case of Facebook, they're using Java and they're trying to make their horrible hackety language called Hack, which is a weird Frankenstein's monster-like language based on PHP, to be more like Java. Java is amazing. So the question then is, well, okay, what can I do to make it more efficient? What can I do to make it scale better? What can I do to make it a better fit? And you've heard me talk about a lot of different things here, right? When it comes to energy efficiency, Java, of course, comes towards the top. There's this great study that was done in 2018 that was covered here in this blog by the News Stack. It shows that Java is in the top 5 most energy efficient languages. Well done. There's the discussion around GraalVM for instant startup time. GraalVM also gives you very, very small memory footprints as well. So Java is doing quite well here. The largest companies on the planet use Java. Amazon, eBay, Google, Facebook, Alibaba, everything. All these companies are all based on Java. Its credentials are not in doubt. But that's not to say it couldn't get better. That's not to say it couldn't get better. Java, historically, that's not to say that it couldn't get better. Java historically hasn't had a great story with respect to threading. Most programs in the Java ecosystem are written with the one thread per request model. You make a request, it goes into the servlet stack. Servlet stack wakes up the servlet that is routed or designated for the route that you've entered. That in turn wakes up whatever component is responsible for handling that request. So in the case of Spring and the dispatcher servlet, it wakes up the Spring MEC engine, and then that in turn finds your controller, which and then there's a method on that controller that it then invokes. So this all happens inside of a thread, which is fine as long as the thing that you're doing in that thread is quick and it's over with quickly, right? But if it's not, then you've got a problem, because historically threads on the JVM have actually been very expensive. They corresponded more or less to operating system threads. That connection meant that if you exhausted the number of, if you wanted to handle more requests, you had to create more threads, and that wasn't so easy to do. It created a lot of RAM and a lot of contention, and oftentimes for no reason. The truth of it is that those threads, hopefully, are doing work most of the time, but that's just not often the case, right? It's so easy to log into a production system today and realize, oh, okay, I've got most of my threads are busy or in a wait state, and yet most of them are also idle. The CPU is idle, which is a bad result. You don't want your threads sat there doing nothing and yet unavailable for anybody else in the system to use. So there's got to be a way to sort of do a thing that might take time, and then as long as it's something that doesn't require the CPU, that is to say it doesn't require the thread, do it off the thread, right? If you're doing Fibonacci, if you're doing cryptography, if you're doing algorithmic things, then of course that requires time on the CPU. But if you're just waiting for bytes to come back from a network request to your SQL database or to another microservice or Kafka or whatever, if you're just waiting, then it seems a real shame to be sitting there on that thread doing nothing, right? Somebody else wants time on that thread to handle work on the CPU. So how can we make our code more scalable? How can we make sure that we're not blocking the ability of the rest of the system to use those precious few threads? And of course, over the years, I've talked about reactive programming, right? Reactive programming is a really powerful way to address this. It gives you a programming model that is, at its core, all about offloading blocking operations so that you only spend time on the CPU when you need the CPU, right? I think it's a really good fit. The problem is it's a different programming model, and a lot of people in the Java ecosystem won't be familiar with that programming model. It's more functional in style. So if you're coming from something like Lisp or Scala or whatever, maybe you're better prepared to write in that style. But if you're coming from Java or Python or something like that, it'll feel a little different. So it didn't register for a lot of people, right? I mean, a lot of people use it and still well used and liked, but it just didn't. It was never going to be mainstream, okay? I think we can all agree on that. It was, even the Spring team, we've maintained both stacks over the years, right? Knowing full well that the majority of people aren't going to use the reactive stack, but for those who are so inclined and who need the scale, It's an option and it's there. But wouldn't it be nice if we could have our cake and eat it too? Lots of other languages have arrangements where they can get that non-blocking scale without the complexity, the implied complexity, the assumed complexity of something like reactive programming, or at the very least without the full-on rewrite required to adapt this new programming paradigm, right? Other languages have something called async await. Kotlin, one of my favorite languages ever, has suspend functions. And these are syntax modifiers that go into your program code that change the structure of the program in such a way that you're not blocking on an asynchronous operation, but it requires pervasive changes to the code. Every place where you do this blocking operation is you now need to decorate the function, the containing function, with the modifier async. And if you want to then invoke that function, you have to say await. And this becomes sort of viral in that if I want to call another function that uses async await, the containing function also needs to be async, right? And so this goes on down the line. It gets to the point where eventually your whole code base becomes mired with these different async await modifiers, which is very invasive and very annoying. And also, you're still using promises. You're still thinking about it in the world of callbacks, right? This is true in JavaScript and TypeScript and a few other languages as well. And so it doesn't feel like it's that much simpler, at least not to me. I feel like I'm still very much in the world of changing the way I write code so that I can make this asynchronous non-blocking flow work. Well, Go has it right. I think Go did a really good job here. Go, which came out, 2008, 2009, something like that, long time ago, it started from the ground up, from the get-go, with non-blocking I/O. And so everything is non-blocking I/O, and then that non-blocking I/O strategy integrates really nicely with Go routines. The result is it's not really possible to write blocking code. You don't have two different paradigms. You've only got the one, and because you've only got the one, it can feel like imperative blocking code as you would write it in Java, but behind the scenes it's not. What's happening there? Well, the runtime, the Go language itself, the Go runtime, is actually managing the threads. And they're not delegating purely to the operating system threads. The runtime itself is doing scheduling, moving your code on and off threads as it realizes you're doing blocking operations. The result is very, very elegant because you don't know you're doing non-blocking I/O. You don't have to care about it. It just works, right? And it seems obvious that this would work. There are only a few things in a typical program that you need to care about, right? I/O, obviously, input and output, fundamentally is blocking. Well, do that in a non-blocking way. Move that off of the thread when it's happening, and then when it's done, when there's bytes available, when there's something to be done on the CPU, put the code back on the thread. The runtime can do this for you. The language can do this for you. It knows when you've made a call to I/O and you've got bytes coming back, but that haven't arrived. It knows that. Same thing for sleeping, CPU spinning, right? If I'm sleeping, there's no need for me to spend my time on that thread. I'm not using it, I'm just sitting there blocking it. That's a terrible waste. Again, if the runtime knows this, it can move me off of the thread, put me in RAM, and then when the egg timer goes off, when I'm done sleeping for however many milliseconds, wake me up, put me back on another thread, and let me continue with the call stack that I had before that, as though I was on the same thread. It's not conceptually all that difficult to do, but it turns out it's very difficult to do this in such a way that it's backwards compatible. You end up introducing, in the case of JavaScript and Python and Rust and C# and so on, you end up introducing a whole other syntax. That's this async await about which we just spoke, right? I wonder if there's a better way. Well, it turns out there is. The Java team, the heroes working on the Java project at Oracle and elsewhere, introduced virtual threads into the JVM for Java 21. Okay, now we're on Java 22 already, so this is a bit of a late look at virtual threads, but I think it's very, very interesting what they've done, because they've done it in such a way that it's both the least invasive of all the languages I've seen, while also being backwards compatible, which is incredibly difficult to do. It's not, it in the sense that there is at least one thing required, one place in in your program. It's a bit more invasive than Go, where there's nothing required, but it is just one thing. You just change it in one place, one time, and then you could do 99% of your work in virtual threads with Java. Okay, so we're going to talk about virtual threads today, what they are, how you can use them, and how they benefit you. And friends, I want to tell you up front, I was really struggling with this. I love virtual threads. It makes a lot of sense, but it's very hard to demonstrate virtual threads, right? Because you kind of, by definition, you need scale, right? And I don't have scale. on my local machine. I mean, the people who benefit from this stuff are the people who are having problems in the first place with scale. Normally, most people aren't having enough problems with modern hardware to notice this, right? Especially if you're doing departmental business sort of applications. It's only these large, super sites, these large mega services that are, billions and billions of users concurrently that will notice these issues. And so the question is, how can we demonstrate it while also making it approachable to understand? And I'm going to be honest with you, friends, I'm not that smart. I'm just not. So today I'm going to steal, really, shamelessly, 2 different demos, and we'll talk about each one of them. And but I want you to know this video was brought to you by me, kinda, and 2 people: Jose Pomar, Professor Jose Pomar from the Oracle Java team, and my colleague, friend, hero, Cora Iberkleit. Okay, and we'll talk about both of those people and their demos soon. So, my friends, let's dive right into it. Okay, first things first, you know what we're going to do. We're going to go to start.spring.io. We're going to build a new application called Threads. I'm going to use Maven. I'll use Java 21 or later. I know this is obvious, but if you want to use virtual threads, you need to use Java 21 or later. It doesn't exist in Java 19. It doesn't exist in Java 20. I mean, technically it does, it as preview features, but that's not what you want, right? Nobody wants to live that life. Just move to Java 21. It's borderline irresponsible to be using anything less than Java 21 at this point. It's free money, people. Just move to Java 21. You're getting an amazing result. Okay, what do I need? I'm going to use the test container support. I'll use GraalVM, native images. I'll use the web support. And that's, you know what? I want an actuator as well. We'll add the actuator for observability. And I think that's pretty much it. Let's go ahead and generate this. Go to the downloads here. And we'll open this up. Okay, so before we get too far down the line, let's just take a look at how virtual threads work in Java, okay? Forgetting about Spring for just a second. You know, I love Spring. Don't worry, we'll get there. But I want to just take a look at virtual threads in the context of the JVM, and I just happen to be doing it inside of this public static void main Spring Boot application. But for our demo, for ease of understanding, I'm just going to get rid of Spring Boot just for a little bit. Don't freak out. It's fine. We're still okay. Everything's fine. But let's just write some regular Java code here, okay? And again, I'm stealing this from Jose Pomar. He works at Oracle as a Java developer advocate. I think he does a great job. He's in France. He's a professor, just a legendary person. Very, very great demo, and I really appreciated him putting it out there. I asked him once if I could borrow it for my demos, and I have joyfully and gratefully used it ever since he gave me permission. And yeah, just amazing. Yeah, just amazing. Okay, so let's dive right into this. So we're going to build an application that launches a bunch of threads. Var threads. Java lang thread. I'm just creating regular Java lang threads, okay? And I'm going to create 1,000 of them. So for var I is 0, I is less than 1,000, and then that, okay? And I'm going to create the threads. I'm going to add the threads to this collection. So which thread? I'll add this one. I'm going to use some new constructors here. We're going to use platform threads, okay? These are unstarted platform threads. And this is more or less this of platform is basically what you would have gotten in the old days if you had just done new thread like that and passed in a runnable, okay? That's the equivalent from yesterday. You can still do that. This is a platform thread, okay? So it's not started yet. We haven't hit start. And we're going to come back to what we're going to do in these threads in a second. But for now, all we need to know is I've created a Java lang thread and I've added it to this collection, okay? Now what? Well, once I'm done with creating all those threads, I'm going to go through the collection of threads in my collection here, and I'll say t.start, all right? And then I'm going to say t.start, and then I'm going to join each of the threads. So that means I'll wait here on line 32 until all the threads have finished, and only then will I be allowed to go to 33, okay? So I'm joining each of them, waiting for them to finish. I won't be able to get to 33 until all 1,000 have finished their work, okay? Okay, now what? Now what would I want to do? Well, I want to take note in the threads of the name of the first thread. This is a ridiculous thing to do if you think about it, right? So I'll go down here, I'll say names.add name, but also names. I'm going to take note of the current thread's name here, right? So thread.currentThread.toString. It's not actually the name really, it's something else. But the point is I'm going to put these names in a set Sets are, of course, a Java, a collection, and they give you something very interesting, which is that they deduplicate elements. So if you add the same element 5 different times, it'll only be available once when you iterate over it. So if I add the number 1 to that set 5 times, and then I iterate over the set, I'll only iterate over one element of type 1 or value 1. Okay? So I'm adding the thread name, and then I'm going to sleep for 100 milliseconds. Okay? And of course this requires try catch, so let's just do that. And you know what? I'll put the whole thing in a try catch just to make it easier to understand. So I'm adding a thread, but I'm only going to add the name of the thread if I'm in the very first of the 1,000 threads. Okay? Again, well, if you're following this is a ridiculous thing to do, right? Think about what I'm doing. I'm launching a thread, then I'm noting the thread's name, then I'm sleeping 100 milliseconds, and then I'm going to do the same thing again, and again, and again. Okay? So think about it like walking down a street, right? Here in San Francisco, we have Market Street. So imagine I'm on Market Street, and I walk 10 meters, right? And I see a sign that says Market Street. Okay, great. I'm on Market Street, and I'm very clearly walking on Market Street. As far as I know, I haven't left Market Street. And then I walk 100 meters, right? A tenth of a kilometer. And I look up again, and there's another sign that says Market Street. Great, I'm still on Market Street. I'm really glad that I'm on Market Street. But of course, I know I haven't done anything but walk in a straight line, right? Well, as straight, at least as Market Street will allow. I haven't changed or veered in any off course or gone in any other direction. So of course I'm still on Market Street. But you know what? It's good to write it down just in case. So every 100 meters, I'm looking up and I'm checking the sign. I'm like, okay, still on Market Street. Very good. And of course it's the same street. So when I add that street name to this collection, it's only going to appear once, right? Because it's the same name. It's the same exact name 5 different times. Why would somebody do something so absolutely, dumbfoundingly weird? Well, because sometimes Market Street isn't Market Street. So let's go ahead and run this. Remember, we're using regular platform threads here. Okay? Restart. All right, as we expected, it's a collection containing one name, two string, which shows that I was on this thread called number 31, which ran on this operating system thread and executor and all that kind of stuff. Okay? But one thread, as we expected, right? It's not surprising. And what that means is that I started on line 25, I noted the current thread's name. Now on all the threads, not just the first one, on all of them I'm sleeping. So I've got 1,000 threads and they all need to sleep, which means that the runtime needs to schedule time on the CPU for all of them to sleep as quickly as possible. Now of course I've got a bunch of cores and I've got a pretty healthy machine, but still this is wasteful, right? I'm wasting 100 milliseconds 1,000 times, right? That's just a waste. Thank goodness I have more than enough cores to be able to make it so that it's negligible. But imagine a single CPU, one single core on one single CPU. You'd have 1,000 times 100, right? So 100,000 milliseconds that you'd have to wait. And then of course the situation only gets worse as you go on, because then it's another 100 milliseconds, another 100 milliseconds, another 100 milliseconds. So you'd very quickly realize that the CPU can't schedule everything at the same time, so they serialize, right? And you'd see this waste. Now, wouldn't it be smart, again, if you could do something where, hey, I'm sleeping for 100 milliseconds, nothing is happening, I'm literally just waiting, and the runtime could see that, and it paused this thread, and it preserved the call stack, so that if I had like var counter equals 0 and all that, and I did this, what if it could preserve the call stack? It knows what came before, and what if it could write up some code so that it puts me after line 29 on another thread, and then it recreates these variables. It puts this value at, let's say it starts at 2 or 1 or whatever. Let's say if it preserves that value and then allows me to get to this place with this value intact, so that this is now equal to 3 as of this point, right? If it could do that, well, then I didn't need to actually sit on the thread wasting time. I could move a lot more quickly. Well, we can do that, right? Of virtual. That's all I've done. I've changed the kind of thread. Now, at the end of the day, the result is still a Java Lang thread, right? I'm still using Java Lang threads. This variable is a Java Lang thread, right? Okay. But all I've done is I've just slept for 100 milliseconds each time, and I'm taking note of the current thread name. I'm only doing it for one of the 1,000. Otherwise, we'd have at least 1,000 results in here. So I'm on Market Street the entire time, and I'm taking note of the street 4 different times. What's happening? Let's see. Oh, look at that. Market Street is no longer Market Street. I was on worker 1, and then I moved to worker 11, and worker 2, and worker 5. Now this is a set. Sets are not necessarily ordered, and in fact, this one is not, so this could be in different orders. And of course, the movement from one thread to another is random. So when I've sometimes run this demo, you'll see that I'm on maybe 3 threads. I've even seen it once where it's on 2 threads, which is complete random. I should play the lottery, right? I'm on this thread, then I sleep for 100 milliseconds. The runtime says, "Oh, hey, you're sleeping. You're sleeping on Market Street. Somebody else needs to walk here." Moves me off of the street, moves me off the thread, puts me in RAM, and then lets me sleep for 100 milliseconds. And once I'm done, it moves me back onto the sidewalk. I wake up and I'm able to keep going. And meanwhile, I haven't been blocking other people's way on the street. So as far as I'm concerned, I went to sleep on Market Street and I woke up on Market Street. But during that time, I wasn't actually on Market Street. And the same thing happened here. I wasn't actually on this thread. I got moved off the thread. But of course, if you look at this, it still says Market Street here, virtual thread 31, virtual thread 31, virtual thread 31, but the actual operating system thread is what's changed, right? Isn't that interesting? So it moved me from one thread, and then it put me on another thread, because the first one that I was using, the first thread that I was on before, it's busy. It's doing something else now. So the operating system and the runtime said, okay, I've got more work for you. Which thread is available? And the runtime put other work on that first thread. So I can't go back to that first one, or at least it's very rare. It's very rare for me to be put back on the same thread that I left, because in the meantime, something else will have taken up the work, right? So I get put on another thread, and that's why you see it 4 different threads. But sometimes, randomly, sometimes the first thread becomes available, and you can get put on it, right? And so you can actually see sometimes it's maybe there'll be 2 elements, maybe there'll be 3, maybe there'll be 4, whatever. And of course, a lot of this is a function of your computer and your cores and all that stuff. So your results will vary, but you can very clearly see that this one thing moved me from one thread to another. Market Street is not Market Street sometimes, okay? This is an amazing result. Now, this is very low level, okay? I had to write threaded code here. I'm literally creating Java threads, right? It's not hard. It wasn't a very big deal. I just did this in one place, and then suddenly all the threads are virtual. And everything that gets done inside that virtual thread, no matter how deep down in the call stack, as long as it's attached to the current thread, is now, there's this magic trick where I can be relocated to another thread automatically, right? The runtime can do that work for me. This is an amazing result, but very low level. Threading is not really great. I encourage people to avoid it whenever possible. Let the framework do it for you. Let the runtime handle this for you, or at least use some sort of structured concurrency model. And it doesn't really matter what. Tony Hoare, who's Sir Charles Anthony Richard Hoare, is a famous British computer scientist about whom much has been written. I'll let Wikipedia do the work for me. You can read this. But he's famous for having, hyperbolically apologized for inventing, quote unquote, the null reference, right? He called it his $1 billion mistake. And obviously, here, he was wrong, right? Obviously, the $1 trillion mistake is PHP. But the point is, that mistake is something about which he's, well cited and quoted and known. But it's not the only thing he did. In fact, it's not even the most interesting thing that he did. He's famous for along with Edward Dijkstra, inventing the dining philosopher's problem and then formulating a solution for it, right? He's also famous for, among other things, the quick sort, the quick select, and so on. He also invented something called CSP, or Communicating Sequential Processes. And he talked about this at first in the 70s. He wrote a book in the 80s, and that book you must read it. And it's an amazing tome. And basically, the result is the way we are doing threads is too low level. It's too dangerous. It's indeterminate. There's no safeguards there to make sure that state doesn't get corrupted. And he's talking about exactly the kind of threading that I just did. This is too dangerous, right? This is too low level. There's no structure to it. So, first of all, you shouldn't be doing this by yourself. Second of all, if you're going to do it, use a structured concurrency approach, like actors, like sagas, like Spring integrations, stage event-driven architectures, whatever, right? And also, at the very least, be a little smart about how you create the thread in the first place. So if you're using Java, you're probably not creating threads directly. You're probably using an executor service like this, right? Well, this is most of the time done so that we have a thread pool executor, right, like that. But you don't even need to do that. You can use a static method here. And if you're using Java 21, you'll notice that there's this new virtual thread per task executor. Well, this is not a thread pool, friends. It's a factory for threads, just like the thread pools of yore, but this doesn't pool threads. It just creates new ones all the time because they're cheap now, right? What they've done behind the scenes here is they've broken the link between operating system threads and Java threads. So I can create as many Java threads as I want, and it's not an issue, right? It's not going to cost me that. I'm not going to run out of operating system threads or the ability to schedule them. And so, in theory, you could create millions of these now. Just create as many as you need, and they can be garbage collected when they're done, right? So this is a bit better, but still, how do you use this in a Spring program? Well, Spring has lots of configuration. Obviously, if you're using a Spring Boot application, you can, let me get rid of all that. I can put all this now, by the way, in a application runner, and we'll just ignore that. Threads 1 demo. Okay, very good. All right, there's the first demo. So Threads 1 demo, close that. Actually, I don't want that to run anymore, but it will run on startup. So if you're using Spring Boot, it's pretty straightforward to define your own executor, right? So I can say executor service, blah, return my own executor service, like so. And that'll get used in a lot of the different places that Spring Boot is looking for thread pools. But there are some well-known beans whose name you have to match and so on. If you're doing @enable async, for example, and you're doing scheduled methods or async methods, @enable scheduling, you can do these kinds of things. If you're doing these kinds of things, then this will get plugged in. There's also threads involved in the threading, web server front-end thread pool, that kind of stuff. There's also thread pools involved in Spring integration. So in general, you just have to know where to plug these in. There's a lot of different places. So to make your life a little bit easier, we've introduced a property, Spring threads virtual enabled equals true. Specify that, and wherever it's useful, including in Spring MVC, we will plug that in. So now, whenever you have one thread per request, it's actually a virtual thread. So if in that thread you call a SQL database and you do I/O, or you call another microservice with the REST client, or you call something else that blocks, it's okay, because behind the scenes, the runtime will detect it and then move you off the thread while you're waiting for this blocking operation to happen. And again, those blocking operations are I/O, they're thread.sleep, things like that. Okay, so this property is really, really key to turning on this feature in your Spring Boot application. So again, my advice to you, friends, is go to your management and say, hey, look, I've got this audacious, bold new idea. I'm going to give us incredible scale. All I need is about 2 weeks' time, no interruptions, and as an added incentive for such incredible work, I want you to consider giving me the money for cloud infrastructure spent that we don't have to spend, right? So for example, if I lower how many services we need to be able to run our Java services, how many servers, and so as an added incentive, I encourage you to go to your management. No, let me say. So this underpins how fast, and let me try again. So this property is really, really convenient. You set the property and suddenly your Spring Boot services will take advantage of virtual threads wherever logical and appropriate. Friends, this is a big deal. You just upgrade your Java program to Java 21, you move to Spring Boot 3.2 or later, which is now almost 6 months old in of itself, and now you get virtual threads. If I were you, I'd go to management, I'd say, hey, look, I've got a bold and audacious new idea. I'm going to give us a lot better scalability. All I need is 2 weeks of no interruptions, and I would suggest, as an added incentive for me, for doing this, for undertaking this incredible effort, if we save money in our cloud infrastructure spend, maybe you could, put that saved money in my bank account as a bonus of sorts, right? Let's see what they say. And if they do it, you just disappear, upgrade to Java 21, do this, and then take the other 13 days off. It'll be fine. Okay, so this is a big deal. We've got virtual threads now. What does it actually buy us, right? And this is where it gets sort of, conceptually what's going to happen, but how much? And this is, my friends, where it gets very difficult. This is one of the reasons why I so hesitated on doing this video, because it's very hard to sort of demonstrate in a vacuum, right? Like I said earlier, it's one of those things where scale really helps you to kind of see the forest for the trees, but it's very hard in a sort of hello world context to see what's happening and how good it is for my average application. So I just showed you the example here in public static void main, thanks to Jose's amazing work. But what about a typical Spring application where you're not just doing arbitrary 100 millisecond thread.sleeps? What does that look like? And you have to bear in mind that testing this is very difficult, because remember, on the Mac you'll get less scalability than you will on Linux, just for scheduling reasons, for example, and also I'm on the same computer, so there's that, and it's very hard to get something that sleeps long enough for you to notice the contention or the scarcity of resources. Also, it helps if you minimize the number of threads you've got, which is not something you do in a typical application. But if you want to force scarcity, you need to force it by limiting the upper bound of the thread. So all of this got me really puzzling. I actually built a whole example and I deployed it to Kubernetes, and it was fairly typical, database access and security and all this kind of stuff, and it was just very hard to sort of isolate. And I really wanted a better way to demonstrate this. So I talked to my colleague Cora. Like I said before, Cora is she's on my team, on the team on which I work, rather, not the team I don't run a team, but if I did, she would be on it. But she's on the same team as I. She's amazing, just amazing. She's a leader, she's a visionary, she's an amazing engineer. Well, she's an amazing teacher, an amazing engineer, an amazing person. Just go look her up, Cora Eberklade, okay? So thank you, Cora Eberklade, okay? And she did this amazing demo at Spring 1 2023, one of the keynotes from last year's Spring 1. And by the way, she'll be at this year's Spring 1 as well, so do not miss that. And she did this amazing demo, and I was wondering if I could borrow that, for this video, to sort of take it and take the parts that I think will be most, because she did a very nuanced, very, very good explanation. So I've taken her code shamelessly, unapologetically, but gratefully, and we're going to reproduce it here today. Very simple, it's not simple, it's just I'm going to put things in, I'm going to consolidate, that's all, okay? So that we can follow it all in one place for our very simple demo here, okay? So let's revisit this now. We looked at virtual threads. Let's create something a little bit more involved, okay? What I'm going to do here is I'm going to create an HTTP endpoint using the servlet stack, of course. I could use a Spring MVC controller. I could use Spring MVC functional style endpoints, but the point is I'm using Spring MVC to expose an HTTP endpoint. Why am I doing that? Well, because remember, I've got this property. If I set the property, then when I make a request inside that servlet, all the threads that are being assigned to the servlet are virtual threads. So I'm going to create these HTTP endpoints. And these HTTP endpoints are going to, in turn, make a network call to a downstream service using the REST client. So you've got two services here. You've got our service based on Tomcat, which does I/O. And it, in turn, those methods, those endpoints, that endpoint that we're going to create, will call another service that's going to block arbitrarily for us. And we're going to use a Docker image that will stand up a Go program, a Go language program, that is a clone of HTTP bin. And it's just a clone of that. It's a nice service that you can use for testing I/O, for testing network effects. And one of the endpoints is designed to just wait as many seconds as you want before returning. Well, of course, this isn't such a big deal, but now the client of that downstream HTTP endpoint is going to be waiting as well. So you can really force your system to run into scarcity of resources by calling this endpoint enough times. We're going to create a simple HTTP router function, server response, HTTP endpoints, and I'm going to return route like that, .build, .get, and we're going to return, we're going to block for a number of seconds here, new handler function, okay? So there's the basic framework. So when you go to localhost, which port, by the way, the Go program will run on port 8080, so we're going to use 9090 for our service, okay? And so when you go to localhost 9090/seconds and you pass in, let's say 3, we will send a request to the downstream Go HTTP bin clone that blocks for 3 seconds. Okay, so far so good. And how are we going to block? How are we going to make those network calls? Well, we're going to use ye old REST client. You can use the REST template as well. I just like the REST client. It's just very convenient. So we'll inject the builder here, and we'll say builder.build. But I'm going to specify a base URL here, since we already know where we're going to make these requests to. And actually, it might even be better to parameterize this. So maybe I'll do that as well. I'll do http bin.url, string URL, and then we'll just use that instead. So here we go. Okay, so not bind, bin. All right, good. There's the URL. So that'll be easy enough to follow. And then we need to actually make the request. And so the logic here for the request is pretty straightforward. We're going to inject the REST client here, server response .ok.body map.of done, let's say true. It doesn't matter, just we need something from the HTTP endpoint. The response is not interesting. It's the time it takes to get the response that is. Okay, and now we're going to make a request to HTTP bin using our REST client. So .get dot URI. I'm going to specify the URI as delay / and then we're going to take in the parameter here. So var seconds equals request dot path variable seconds. Okay. And well, seconds, put that in there and retrieve it and then turn it into an entity of type, let's say string. Okay. We don't actually care about the results. And that's it. And so we want to log out where we are in the system. So let's go ahead and do that here. I'll var log. I don't know. I always get, it's sort of, who cares? Okay, get that. Very good. Log info. Okay. On this. And we'll say the result, request to the bin, get status code. Okay. .toString. And then thread dot current thread dot toString. Okay, and so it doesn't support parameters. Okay, well, in that case, I do care. Logger dot get logger factory dot get logger get class. Good. Okay, that looks happy. All right, good. So we've got this, and this. I guess we can remove that and remove this. Very good. So now we've got our simple HTTP endpoint. This is a Lambda, of course. There you go, much nicer. But you understand what's happening, right? Somebody calls our localhost 9090 / seconds. We then make a network call to another host and port, which is a Docker image that we're going to run on our machine on port 8080 / delay. And that's going to wait for as many seconds as we specified here. Pretty straightforward. And we're going to get the response. We're going to print out the status code and the current thread. We don't actually care about any of this. I mean, it's just nice to look at this, but this isn't all that germane. But it's because we're going to make so many requests, we're not going to be able to really, besides confirming that everything's okay, we're not going to really inspect all this stuff too much. Okay. So now, this is our service. Let's go ahead. We can run that, but I want to run it. I want to create a test here, and we need to before we run this code, we need to also spin up the Docker image. So we'll go here. I've got this. Fine, don't care about that. I've got this. This is what I care about here. This is our test code, and in this test code, I'm going to run the Spring Boot program. Get rid of that. Spring application dot run demo application or threads application dot class. We don't, we can just pass in nothing there. It's fine. Okay, we can run it, but I want to set up some things before we run it so that we can parameterize it per run. So actually, maybe we'll do this. We'll do static void run with virtual threads boolean virtual threads. Okay, and obviously we need to run the Spring Boot application. But before we do this, we run the Spring Boot application. So we're going to say true with. Actually, we'll do false first, so we know what not to do. Before we run the Spring Boot application, let's set up some context here, some things to make this a little easier. So first, what port are we going to run our container on? Port 8080. What is the container? We're going to create a new test container here, like so, and it'll be mccutchen go http bin. Okay, there's that. And this, by the way, very convenient. Cora found this, obviously, and I'm a big fan. So it's a Golang port of the venerable httpbin.org HTTP request and response testing. And so it's just you can get, base64 decoding and encoding. You can return, it's like echo, you can pass something in and get it returned back. You can return 200 unless there's a header. You can get a cookie. You can delete stuff. You can deny something by robots.txt. Do form posting, get headers, return an image, all sorts of stuff here to test your HTTP functionality, even WebSockets. Wow, look at that. And the one that we're using is delay. So there it is. So delay responds for the lesser of either n or 10 seconds. So if you specify 9 seconds, it'll wait 9 seconds. If you specify 10 seconds, it'll wait 10 seconds. If you specify 1 second, it'll wait 1 second. If you specify 20 seconds, it'll wait 10 seconds, right? So very, very convenient endpoint. That's what we're going to use here. We're going to make this call to delay / seconds, okay? So we want to run this with exposed ports. That's the port. And we're going to wait for, whatever. Wait all strategy, fine. Okay. And then we want to start it. So we'll say HTTP start. Good. Now we've got a Docker test container. Okay. Now we want to start the application itself, but we need to specify some properties. So how many threads do I have? Well, I don't have a number of threads per se, but processors is a nice number to know about. Okay. So we'll do that. And then this is a string that we need. Pass that in. Very good. And so we've got some properties to set. And I'm going to set these as system properties. And these system properties will be available in Spring Boot as though I had specified them in application.properties, right? So this is a nice way to specify some things. So, okay, first things first, how many threads do we have? Server.tomcat.threads.max is equal to threads, okay? And what about JDK, the virtual thread scheduler, the max pool size in the JDK itself? So JDK.virtual threads thread scheduler dot max pool size, okay, and that's that. And then what about the enabling of the virtual threads in Spring Boot? Well, again, I'll say spring.threads.virtual.enabled is equal to this boolean that we're passing here, right? Boolean dot toString virtual threads, okay? And then finally, what is the HTTP bin URL, right? Well, it'll be system.setProperty HTTP bin.url, and we're gonna get that port. So it is get host, then this, then HTTP bin, get mapped port. Okay, so we're gonna pass in, we're gonna start the thing on port 8080. There's a mapped port behind the scenes, which might be something else that Docker has created, and I'm gonna forward the request to that mapped port. Okay, so this property, this is what we're injecting over here in the production code, right? We're injecting it here, HTTP bin.url. So here, there you go. Okay, and so we're going to set the property to true or false based on this boolean, and then that'll enable the key Spring Boot property, spring.threads.virtual.enabled, spring.threads.virtual.enabled. And then this will enable the property spring.threads.virtual.enabled. You'll see that here. So I'm not doing it in the property file, right? I'm doing it in the system, but that'll get, it'll become part of the Spring environment, and it'll set the property for us. So we go here. Spring.threads.virtual.enabled is equal to true or false. Okay, so we've got our method. Now let's actually use this. We're going to run it false, so it's not going to be enabled, but it's going to be the exact same setup. And then, of course, we're going to kill the JVM. That'll kill the Docker image, and it'll kill the Spring context there. Okay, actually, that's all pretty straightforward. Let's go ahead and run it. Let's see what happens. So we're running the test code, which will launch the production code, but only after we've specified some properties and only after we've launched our Docker image. Okay. Everything's up and running. We've got the Docker image here. You can see that. But we've also got our Spring Boot application. So now let's drive some traffic. And to do that, I'm going to use any of, you could pick anything, right? One of the things that Cora used, which I quite like, is Hey. But there's also another one called OHA, O-H-A, that you can also use Apache Bench. And they all take basically the same parameters. They just do different things in the output. But even there, they measure a lot of times the same things. So you pick whatever you want. I'm going to use OHA. This is a Rust language client, and it'll give us some interesting results. So the two things they want is the concurrency, like how many threads you want to have at the same time, and then the number of requests total. So I'm going to ask for 20 requests at the same time. I'm going to ask for 20 requests at the same time, and I'm going to make 60 requests. Again, super important to remember, these are low numbers. But they're low because they create scarcity, right? I've limited the number of threads here in my system, and I've got a large amount of concurrency, and also each request is going to take 3 seconds, right? That's the problem here. If I make a call to /3 in my production code here, remember, /3, it's going to block. It's going to wait for 3 seconds. So it's not about what happened. It's not about creating a billion threads, although that's interesting too, and you certainly can do a better job of that with virtual threads. But what we're trying to do is, given a fixed upper bound for the number of threads, which one finishes first, right? And you can imagine if all the threads are sleeping, then there won't be a lot of threads in the thread pool to pick up the excess work and help drain off the queue of work because they're all busy sleeping, right? So you're going to have to just wait for those to finish at some point. Whereas with virtual threads, as soon as you hit a block in the action, then it gets moved into RAM and somebody else can use that thread. So you get to do more work in the queue faster. Okay, so we've got this. Let's go ahead and use OHA. So number of threads, I'm going to do localhost 9090 / and let's say 3 seconds. Okay, let that run. Oops. Okay, so let's say localhost 9090 3 seconds. So before we run this, let's just go back and make sure I didn't miss anything obvious here. So HTTP bin.url, we're setting that here. That's going to be the host name. That's not the full URL though. We need this thing right here. Okay. We've got the virtual threads, max pool size, everything's good. Got the container. Okay, let's go ahead and run this. Okay. And then we'll go back to our command line and run some requests. Okay. Still running. Okay. So you can see it took a long time because of course these requests all take 3 seconds or more to finish, right? And the total time to finish all 60 requests with 20 concurrent threads was 12 seconds, okay? They finished all 100 of them, all 100% of them, you know, so it's all of them succeeded, it's just it took a while, right? Which we know, that's the whole point. So these are in red because it's a long time, but that's not our fault, that's the downstream service. And remember, I'm using a downstream HTTP service, but this is true for anything that does blocking input stream, output stream IO. Input stream.read is a blocking operation. The bytes that are coming back from JDBC, the bytes that are coming back from the REST client for any downstream service, even the bytes that you send out, output stream.write, if they're not acknowledged and buffered and sent, those can block. And so this is going to take 12 seconds, and this is without virtual threads. If we go, to, what we should have done? Wait, let's run that again, and we'll do exposure, includes everything, always, probes, true. We're going to restart with the actuator module enabled, and we'll rerun the test, okay? So let's go to the actuator first, localhost 9090 actuator metrics, and you can see here that we've got an enumeration of the different threads that are live in the JDK right now, okay? And it says right now there's 26 threads in some pools that are ready to go, rearing to handle traffic. Rearing to handle traffic. This number, I don't know how it's calculated. I imagine that 20 of them are from that thread pool, but what about the other 6? Operating system threads, whatever. This, by the way, is coming from JMX. If you go to JConsole and then open up JConsole and you look at the JDK's thread pool, you'll see this basically the same number. So you go here, JConsole, and then our Java program is this, insecure connection, sure. And you can see threads right now. Let's see if we go here, 34. Okay, so I haven't done anything yet. This is up to 34 now because I launched JConsole presumably. And you can see the peak right now is 34, live is 32. All right, so if we go back here, it says 32, etc. So it's doing stuff with threads behind the scenes, just starting up the JDK. So now you know how many live threads we've got before we've run OHA again, okay? And again, we haven't enabled virtual threads. So now, okay, now if we go back here, run one more time, okay? Go back to the live threads, 39, right? 39. So you can see it's created extra threads to handle the load because there's not enough threads to handle the work otherwise, and it still took 12 seconds. Okay, so now what happens if we go here and run the same program again, this time with true. So we want to enable virtual threads. Okay, here we go, restart, okay, up and running. And so what happens if we reconnect? Okay, cancel, let's just close this and find the new one. Okay, insecure, sure. Live threads is 25. So 32 now. This is 32 over here as well. So okay, so we've got, I think the act of launching JConsole in turn adds more threads, which kind of makes sense, right? So you can see these numbers are basically mirror images of each other still. So 28 threads though. Basically this is where we settled in the beginning of the non-virtual thread enabled demo. But let's drive some traffic and see if this changes anything. And remember, without virtual threads, this took 12.17, almost 12.2 seconds, okay? And the slowest was 6 seconds, and the fastest was 3-point-something seconds, so just over 3 seconds, assuming the ideal case. Let's write this down. So no virtual threads, okay? And now let's run it again, this time with virtual threads enabled. Okay, so that took 9.1 seconds to finish the same amount of work, okay? And we got all of them were made successfully. We did almost double. This is 3.6 seconds. Sorry, this is 3.6 requests per second. Here we were able to do 6.5 requests per second, right? So almost double the number of HTTP requests per second we're able to get handled. The total time was 9.1 seconds for all of the requests. The slowest, again, was basically just a little bit worse than the fastest in the previous run. The average is 3.0 versus 3.6. And the slowest in the old one was 6.1, so almost double the amount of time we were blocking. Whereas in this, the slowest was just a little over 3 seconds, right? They're all basically over, just a little over 3 seconds. That's amazing. That meant that there's no this is double the amount of time we were blocking. So we made a request that should have taken 3 seconds and it took 6, and yet over here, none of them did. So this is a great result, right? The total time, 9.15 versus 12.17, right? Full 3 seconds and some change more to run without virtual threads. And it's the same number of requests. So now extrapolate, right? This demo obviously is a little forced. That's the point. It's a demo, but you can see what happens given predictable contention, what the effect on the runtime is. This is an amazing result. And what did I do to change this, to get this benefit? Was it months of hard engineering and all that to save, what is that, a quarter, right? 25% of my time is now, I got the same amount of work done in 25% of the time. I got double the number of requests per second, right? That's amazing. What did I do to get those incredible results? Nothing. Spring.threads.virtual.enabled. An amazing, amazing result. My friends, there has never been a better time to be a Java and Spring developer. Hopefully, you are so persuaded. And by the way, this works in GraalVM. So build a GraalVM native image, and then take a tenth of the RAM footprint, then do this. You get amazing scale for free. Go to production. Enjoy. My friends, have a great time. Have a great week. And as always, we'll see you next week.